Hello everyone, welcome back to another video. In today's video, we will have a look at bitwise operator. We have already seen what are bits. It is the smallest storage unit which can store data. Usually we store 1 or 0 inside a bit. If we want to perform operation on these bits, we can go for bitwise operator. It is used to perform operation on individual bits of non-decimal number. It can be used to perform operations on non-decimal numbers only. That is data types like byte, short, int, long. So there are four types of bitwise operator: bitwise AND, bitwise OR, bitwise XOR, and bitwise complement operator. So we will see these operators one by one. Before moving ahead with the coding examples, let us see how decimal number is converted into binary number. So here we will see decimal to binary conversion. 59 is the number. Base 10 means it is represented in decimal number system. So we use base 10 to represent a decimal number. So how we can convert this number to binary number system? First, we have to divide this number by 2. Why only 2? Why not other number? Because we want binary representation of this number. And in binary, there are only two numbers, 0 and 1. So we have to divide this number by 2. So we have to divide this number until we get the quotient 0. So first we will divide 2 multiplied by 29 is 58. So we will get remainder as 1. So 1 will be the remainder. Again divide this 29 by 2. So 2 multiplied by 14 is 28. Again we will get a remainder as 1. Again we have to divide this 14 by 2. 2 sevens are 14. Now the remainder will be 0. Again 2 threes are 6. So the remainder will become 1. Again we have to divide this 3 by 2. So we will get remainder as 1. Now again we will divide this 1 by 2. So the quotient will be 0. So we have to divide till we get this quotient as 0. And now the remainder will 1. Now we have to stop since we got 0 here. Now we have to read this number from down to upwards, that is most significant bit to least significant bit. We have to write in this way. So binary representation of 59 will be 1110111. We have to write it from below, 111011. I hope it is clear. Now you might have a doubt, like in Java, this 59 is by default an integer data type, and integer data type is having 32 bits of space allocated to it. But in our case, when we see this binary number, we only have 6 bit, 1, 2, 3, 4, 5, 6 bit. So what will happen to the remaining 26 bit? So all the remaining 26 bit will be 0. So it will be on the left side of this number 0. All 26 bit will be 0. But since it is 0, we don't have to mention it here because already it is 0, and if we are not writing it, then also it's fine. Now we will see the binary representation of decimal number 26 having base 10. So again, we have to do the same procedure. We have to divide 26 by 2. So 2 multiplied by 13 is 26. We will get remainder 0. Again, divide by 2. 2 6 are 12. Remainder will be 1. Again, divide by 2. 2 3s are 6. Remainder will be 0. Again, divide by 2. 2 1s are 2. Remainder will be 1. 2. Now again we have to divide by 2. So finally we got our quotient 0. We have to stop when we get 0. So 2 zeros are 0. Remainder is 1. Now we have to note this number from downwards to upwards. So from most significant bit to least significant bit. So the binary representation of decimal number 26 is 11010. Again, this is also 32 bits and we have only 5 bits. So the remaining 27 bits will be 0, which will be on the left hand side, but we don't have to write it. Now we will see binary to decimal conversion. So we have this binary number and we have to convert that number to decimal number. How we can do that? So I have written these number inside these boxes. So this is the most significant bit which is on the left side, and this is the least significant bit which is on the right side. And this index of this number is, this is at zeroth position, this is a first position, second position, third position, fourth position, fifth position. So we have to start from the least significant bit, that is zeroth position. We have to take this number 1 multiplied by 2 raised to the index of this number. So index is 0 because it is at the zeroth position. So 2 raised to 0 plus take the second number 1 into 2 raised to 1 because it is at the first position. Similarly, we have to repeat it for all the remaining bits. 0 multiplied by 2 raised to 2. 1 plus 1 multiplied by 2 raised to 3 plus 1 multiplied by 2 raised to 4 plus 1 multiplied by 2 raised to 5. So if we add all these number, we will get 59, which is the decimal representation of this binary. So I hope it is clear. Now you can also see here, if we take the remaining 26 bits which are 0, anyways it will be equal to 0 only when we will start multiplying it. For example, 0 into 2 raised to 6 because the next number will be 0. So 0 into 2 raised to 6, anyways it will be 0. So no need of taking the remaining 26 bits. So we have seen how binary number is converted into decimal number. Let's see for 26 how it is converted. So this is the most significant bit. This is the least significant bit, and this is the index position 0, 1, 2, 3, 4. Now again we have to repeat the same procedure. Take 0 multiplied by 2 raised to 0 plus 1 multiplied by 2 raised to 1 plus 0 multiplied by 2 raised to 2 plus take this 1 multiplied by 2 raised to 3 plus take this 1 multiplied by 2 raised to 4. When you will add this number, you will get 26. Now you might have questioned why we are multiplying it by only 2, why not other numbers? Because again it is a binary number system, so we have to multiply it by 2. Because in binary there are only two numbers, 0 and 1. So now that we know how decimal to binary and binary to decimal conversions takes place, we will move on with our bitwise operator. These are bitwise operator tables for different operators, that is for AND operator, XOR operator, OR operator, complement operator. This is exactly similar to logical operator. Just the changes, instead of true we have 1, instead of false we have 0. So we have already seen logical operators. So instead of true, we have to take 1. Instead of false, it will be 0. Rest remaining everything will be same. So we will see how to use it. Let's take a previous example for decimal number 59. Decimal number 59 can be represented like this in binary number system. Similarly, decimal number 26 will be represented like this in the binary number system. We have already seen in a previous slide. So suppose we have to perform AND operation on these two numbers. We will write the binary representation of 59 and 26 one below the other. And since 26 is of 5 bit, I will add one more 0 at the preceding end to align these numbers. So now we will perform our AND operation. So 1 and 0. So if we look at the table, 1, 0 is 0. So we will get 0. Now 1, 1. 1, 1 is 1 inside the AND table. So we will write 1. 0, 0 is 0, 0 is 0. Now 1, 1 is again 1. Again 1, 1 is 1. And 1, 0 is again 0. So this is the output. So again, if we see 11010, so this is same as 26, so it will be 26. If we convert this binary to decimal, we will get 26. Now let's see another example for OR operator. Again, we will write down the binary representation. Now 1 or 0. If we look at the OR table, 1 or 0 is 1, so 1 or 0 is 1. 1 or 1 is 1, so again 1. 0 or 0 is 0. 1 or 1 is 1. 1 or 1 is 1. 1 or 0 is 1. So we got the output. Now this will correspond to 59. If we look at the binary representation of 59, this is same as 59. So this will be 59. Now we will see example for 59 XOR 26. So this is the table for XOR. 1 XOR 0 is 1. 1 XOR 1 is 0. Now 0 XOR 0 is 0. 1 XOR 1 is 1. Sorry, 0 XOR 0 is 0. 1 XOR 1 is also 0. 1 XOR 1 is also 0. Again, 1 XOR 0 is 1. So this will come out to be 33. If we convert this binary to decimal, we will get 33 as the output. We will see bitwise complement operator. So this is a bit tricky. So here I have written the entire 32-bit representation of the number 59. Why I have written in entire 32-bit representation? Because in complement operator, what it does, it will make 1 as 0 and 0 as 1. So it will take the number 1, it will convert it to 0. And if the bit is 0, it will convert it to 1. So as we already know, for number 59, the remaining 26 bit is 0. So obviously it will be converted to 1. Now as it is converted to 1, we have to take this bits into account. So this is the 32-bit representation of the number 59. Now to get the complement of 59, there are two steps involved. First is invert all the bits to get ones complement. So what is ones complement? Ones complement is basically inverting all these bits. That is called ones complement. So take this bit, invert it to 0 if it is 1 and invert it to 1 if it is 0. So 1 will become 0, again 1 will become 0. Here we have 0, so it will become 1. So triple 1, we will get 3 zeros, and remaining all the bits are 0, so remaining all bits will become 1. So this is called ones complement. Now to get the twos complement, we have to flip the bits again and add 1 to get twos complement. So we have to flip this bit again. So basically take the original representation and add 1 to it. So addition of bits is done like this in binary. 1 plus 1 is 10. So we will write 0 here. 1 will be carry. So again 1 plus 1, 10. 0 will be here. 1 will be carry. Again 1 plus 0. 1 plus 0 is 1. So 1. Now 1 as it is, we will write the entire number because we don't have anything to add. So this is the output which we will get when we do complement of 59. So this will come out to be minus 60. Now how we got this minus 60? Now we all know that if we convert this binary representation to decimal, we can get 60. But why minus? Because in one's complement, if we see the most significant bit, that is the leftmost bit, that is 1. So 1, this bit represent negative or positive. If it is 0, it will be positive. If it is 1, it will be negative. Since in one's complement this bit is 1, we have to take it as negative number. So this number will be minus 60. So let's open the IntelliJ IDEA and we will see all these operations there, and we will see whether this output is correct or not. So I have opened my IntelliJ IDEA. I will go ahead and create a new class in source directory. So class name will be Bitwise Operator. So my class, I will close these tabs. So my class is ready. I will go ahead and create a main method. Now we will see the first operator, AND operator. We will see whether we are getting this output as 26 or not. I will comment as AND operator, bitwise AND operator, and we will see whether we are getting the desired output or not. So 59 and 26. Let's run this code. So as you can see here, we are getting the output as 26. So here too, we are getting the output as 26. Now we will see what we are getting for 59 or 26 operation. So second one will be bitwise OR operator. We'll comment this piece of code. Let's see 59 or 26. So we should get output as 59. Let's run this. Yeah, we are getting output as 59. Now the third operation is 59 XOR 26. So in this case, we should get output as 33. So let's comment this code and let's try to see the third operation, that is bitwise XOR operation. So if I do 59 XOR 26, I should get output as 33. Yeah, I'm getting output as 33. So we can see we are getting the desired output. Now let's see the final operator, that is bitwise complement operator. So we will see complement 59. Bitwise complement operator. Let's print complement 59. So here we can see we are getting minus 60, which is the desired output. So I hope it is clear. Okay, so we have seen these four bitwise operator, but now you might have a question like, okay, we know these operators, but what is the real-time use or how to use this operator in coding? So we will see a few examples where we can use this bitwise operator. First, I will comment this piece of code. Suppose I want to determine whether a number is odd or number is even. In that case, for example, if I take this 26, let's copy this 26. So I want to determine whether this number is odd or even. So bitwise representation or binary representation of 26 is this number. So to determine if this number is odd or even, we can simply do AND 1. So the binary representation of 1 is 0, 0, 0, 0, 0, 1. So in binary, 1 is represented with this number. If you take any number and do bitwise AND 1, you should get output as 0 if that number is even. So let's calculate if we are getting output as 0 or not. So for that purpose, we will do this calculation. So 0 and 1, if we go to our table, 0 and 1 is 0. So we will get 0. Again 1 0 is 0. Again 0 0 is 0. Again 1 0 is 0. Again 1 0 is 0. So yeah, we are getting output as 0. So we know that this 26 is an even number. Let's see another example. Let's see for 59. So if we check for 59, the binary representation of 59 is this number. So if we do and 1, bitwise and 1 for this operation, again and 1 will be represented by this number. So this is the binary representation of 1. Now we will perform this operation on 59. So let's see what we get in the output. Again 1 and 1 is 1. We can see the table. 1 and 1 is 1. Now 1 0 is 0. 1 0 is 0. Now again 1 0 is 0. Now again 1 0 is 0. Now again 1 0 is 0. And one more 0. We will get one more 0. So 1 1 we got 1. 1 0 is 0. 0 0 is 0. 1 0 is again 0. 1 0 is again 0 and 1 0 is again 0. So we are getting output as 1. It is not equal to 0. So for any number you can check. If the number is even, you will get output as 0 for even number. And if the number is odd, you will get non-zero output. So this is odd number. Using this logic, we can write a code. If suppose I am taking a variable of integer type having number suppose 63. My number is 63. If num and 1 equal to 0, print the num the number is even, right? If we are getting output as 0, we should write, if we are getting output as 0, we should print the number is even, else if we are getting any other output, we should print the number is odd. Now let's run our code and check whether we are getting the correct output or not. For this number, we should get the number is odd. Let's run this code. Yeah, we are getting number is odd. Now if I make this number as even, 632 is even, let's run. We are getting the output as number is even. So this is one of the use case for bitwise AND operation. You can write the same logic using bitwise or bitwise XOR operator, but little bit logic will be different. But we will not be seeing those cases because bitwise operators are not much widely used because of the readability issues, although they are very fast because they directly manipulate at the bit level. So you should just know like you can do such operations using bitwise operator. So this is one example where you can make use of bitwise operations. Another, we will see one more example. First, I will comment down this piece of code and we will see. I will just write one comment. Even find number is odd or even. So we have seen this example. I will just comment this piece of code. Now we will see another example where I want to swap two numbers. Suppose I have a number int, integer type, variable name is a, number is 50. And I have another number integer type b having value as 75. Now I want to swap these numbers. I want to make a as 75 and b as 50. Swap to 75. Swap to 50. So I want to make a as 75 and b as 50. Swapping two numbers. So for swapping two numbers, you cannot directly go and write a equal to b and b equal to a. What will happen in this case? Suppose if you are writing a equal to b, so a's value is 50. Now we are assigning b into a, so a's value will become 75. And in the second scenario, b equal to a. Now a is already 75, so b will also become 75. So we are not able to swap because the number is lost. This 50 is lost in the first step only. Here we are assigning b's value into a, but we are losing 50 because we are not storing this 50 anywhere. So how we will be able to retrieve this 50? For that case, we will need another variable. Suppose I will need another variable in c equal to suppose 0. Now before swapping, I will put a's value into this c. So c equal to a. Now here what will happen? A's 50 is getting stored into this C. So C will contain this 50. Now A equal to B. So B's value I am storing in this A variable. So A will become 75. Now B equal to C because we have stored A's value into C. So C will now B will become 50. So we are able to swap like this. So if I print this value of A and value of B, we will be able to see the numbers are swapped. See, value of A has become now 75, B has become 50. We are able to swap, but in this case we are using an extra variable C, but I don't want to use this extra variable. I want to avoid using this extra variable. So how I can do that? I can make use of bitwise operator XOR. So we will see how we can make use of bitwise XOR operator to swap this number without using this extra variable. So I will first comment this piece of code and we will see how it's done. Swapping two numbers using bitwise XOR operator. So suppose I have a number 5, its binary representation is 101, and another number 10, its binary representation is 1010. So I want to swap these two numbers. 10 is inside X and 5 is stored inside X variable and 10 is stored inside Y variable. So I want to make X equal to 10 and Y equal to 5. So how I can achieve this without using any extra variable? Using XOR operator. So first step is I will do X equal to X or Y. So what will be the result of this operation? So X is 101. So let's copy 101 and 1010. So here 0 will be there for alignment purpose. Now if we see this code, we will get output as 1 XOR 0 is 1 XOR 0 is 1. So we will get 1. Now 0 XOR 1 is 1. 1 XOR 0 is again 1. 0 XOR 1 is again 1. So we get output as 1111. So this is equivalent to 15. If you convert this binary representation into decimal representation, this will be equal to 15. So the value of X is X has become 15. Now second step is Y equal to again X or Y. So let's see what we will get output. Now X has become 1111 and the value of Y is still 1010. I will comment this first. So again we have to perform this operation. So the value of Y here will be 10 will be 1, 11 will be 0, 10 will be 1, again 1 will be 0. So this is 5. This is the binary representation of 5 we can see here. So this Y has become now 5. So one swapping is done. Value of Y has become 5. Now again we will do X equal to X or 5. So here we can see the value of X is 15. X is this only. So we will copy this. But Y has become 0101. Now we will again perform this XOR operation and we will see the output. Now this will be the value of X. Let's see what we get. So 11 will be 0, 10 will be 1, 11 will be 0, 10 will be 1. So as we can see, this is the binary representation of 10. So the value of X has become 10. So by doing this x or y 3 times, we are able to swap the values. Now the value of x has become 10, value of y has become 5. We started with value of x is 5, y is 10. So this is the logic behind XOR bitwise XOR operator for swapping two numbers. Now we will code and we will see whether we are getting the desired output or not. Let's take the variable x equal to 5 and y equal to 10. Now do our operation x equal to x or y, y equal to x or y, and again x equal to x or y. Now if we print the value of x and the value of y, we should get the swapped numbers. Let's run this code. See, the value of x has become 10, the value of y is 5. The numbers are swapped. So this is how you can make use of bitwise XOR operator to swap two numbers. So these were a couple of examples where I have shown you the real-time use case of bitwise operators. In this video, we have seen all the four bitwise operation and how the manipulations are done at the bit level. And we have also seen the real-time use case of bitwise operator. I hope it is clear to you how these operations are performed. And if you have any doubts, you can mention it in the comment section. Till then, see you in the next video. Thank you for watching.